Hello, Mr. Price here, and this is the final question on the June 2006 Mechanics 2 paper. And this one is another collision and a little bit of energy as well. Let's take a look. So, we have two uniform spheres with the same radius, and we have masses for A is 2 kilograms, and we don't know the mass of B, and they're travelling in a straight line on a smooth horizontal surface, which is important for knowing if the velocities are going to change, so they're not, and with a speed of 5 meters per second when it collides with a stationary sphere B. And as a result of the collision, sphere A continues in the same direction with a speed of 2 meters per second. Okay, and our first question is asking us to find the greatest possible value of m. Okay, now this is a slightly unusual question. It's maybe one that you haven't seen before, but as with all mechanics questions, we're going to want to do our diagram. So, here's sphere A and sphere B, and this one is travelling towards A at a speed of 5 meters per second, and this one is stationary, and then afterwards, do we know what happens afterwards? Sphere A continues in the same direction at a speed of 2 meters per second, and this weighs 2 kilograms, and this is m, and we do not know VB. Okay, now to help us model this, there's a few ways you can do this. We can either say that for the maximum value of m, the particles would coalesce, but the way that I prefer to think of it is just using the information that we've previously been using. Now, if this collided with a perfectly elastic collision, then it wouldn't take much mass to make this sort of get projected a lot, okay? So if with an elastic collision, m doesn't have to be all that big to make big changes. So what we're going to say is we're going to have this as an inelastic collision, okay, as inelastic as we can get. So we're going to say that, okay, so for greatest m, E will be 0, so it will be a very inelastic collision. Okay, so 0, or the coefficient of restitution, will be the separation speed over the approach speed. Okay, so it's going to be separating at VB minus 2, and it was approaching at 5. Okay, but this doesn't really matter, so if we multiply that by 5, so we'll get 0 equals VB minus 2. So therefore, VB equals 2. And this is for the greatest value of m. So now, using conservation of momentum to the right, we'd get 5 lots of 2 plus 0 lots of m equals 2 lots of m plus 2 lots of 2. So let's do some solving here. So 10 equals 2m plus 4. So 6 equals 2m. So m equals 3 kilograms. Okay, and that's job done for part I. Now for part 2, we're now told that actually the mass is 1, and we want to find the coefficient of restitution between A and B. So the actual coefficient of restitution, not our assumed one for greatest n. So, on our force diagram here, we can now change this to 1, and using our E equals separation speed over approach speed. So we get this equal to VB minus 2 all over 5. And we want an equation for VB. So conservation of momentum to the right. We've got 10 equals VB lots of 1 plus 2 lots of 2. So this gives us a VB of 6 meters per second. So we can change this now to 6. So 6 minus 2 all over 5. So this is 4/5. Okay, finally, for part 3, we need to find the kinetic energy lost due to the collision. I'll need a new bit of paper for this. So we're given a different situation. On another occasion, A and B are travelling towards each other with speeds 5 meters per second when they collide directly. Find the kinetic energy lost due to collision. So this is a whole new question. Ignore everything we've done previously. So, a new condition. Particle A, particle B. This is 2 kilograms. This is 1 kilogram. Travelling at 5 meters per second and travelling in opposite directions 5 meters per second, and we do not know VA or VB. So step 1, conservation of momentum to the right. So 5 lots of 2 plus negative 5 lots of 1 will equal VA lots of 2 plus VB lots of 1. So we'll tie it up a little bit. So 10 minus 6 equals 2VA plus VB. So 4 sorry, that's meant to be 5, beg your pardon. So 5 equals 2VA plus VB. Okay, we've gone as far as we can with this. Now let's use our coefficient of restitution. So E equals separation speed over approach speed. So they're separating at VB minus VA, and they're approaching at 10, so 5 minus 5. Okay, so VB minus VA all over 10. Now, these spheres are still the same, they're just travelling at different speeds. So we know that the coverage of restitution was 4/5, so 4/5 equals VB minus VA all over 10. So now we can rearrange this to get an equation that we want. So let's do 5 minus 2VA equals VB and substitute that into here. So 4/5 equals 5 minus 2VA minus VA all over 10. So we get multiply out by 10, so 40 over 5. Right, that's 0.8, so that's going to be 8 equals 5 minus 3VA. So subtract 5 from both sides. 3 equals minus 3VA. So the velocity of A is -1 meter per second. So now we know this one was actually travelling in the other direction, so -1 meter per second. And now substitute this back into here. So 5 equals 2 lots of -1 plus VB. So that's going to be -2, so 5, 6, 7 equals VB. So this is now 7. Okay, now we know the speeds, we can work out the kinetic energy. So, kinetic energy before was half of MUA squared plus half MUB all squared. So this is half of 2 lots of 3 no, sorry, they were travelling at 5, weren't they? 5 squared plus half of 1 5 squared. So its kinetic energy before was 37.5 joules. So the kinetic energy after was half of 2 lots of 1 squared. Okay, we don't really care about directions at this stage. Plus half of 1 lots of 7 squared. So kinetic energy after was 25.5 joules. So kinetic energy lost is simply this, so that subtracts this, which gives you 12 joules. And that is question 8 done, and all of this paper concluded. I hope this was useful. Watch out for future videos on future papers. Thank you.